Okay, this is the third video in this series from section 7.5 about the defective matrix A when trying to solve the system x prime equals ax. So in this example we have an eigenvalue with algebraic multiplicity 3 but two linearly independent eigenvectors. And so we're going to need a third vector who is going to be the generalized eigenvector. So the geometric multiplicity is 2, while the algebraic multiplicity is 3. And so therefore it's a 3 by 3. And so for the two linearly independent eigenvectors, we're going to then build the two solutions that come from them. We're going to find the eigenvector v and the eigenvector w, and then the lambda there is going to be e to the lambda tv and e to the lambda tw. Now for these solutions we have to call them by this strange notation here: x0 upper 1 and x0 upper 2. x0 is going to come from your regular eigenvectors, and then x1 will be the generalized eigenvector. We're going to need another solution, x1, that is linearly independent to x0 upper 1 and x0 upper 2. And just like from the previous example, it gets built under the same principles that we need to find a v1 and a v0 that satisfies a set of equations. We need the v1 to be a generalized eigenvector, so a minus lambda I quantity squared v1 equals 0. Make sure that it's not an eigenvector itself. A minus lambda I v1 is not 0. And then what a minus lambda I v1 is actually v0. v1 needs to be linearly independent of v and w. That basically comes from this statement here. And then v0 is built off of v1. A minus lambda I v1 is equal to v0. And v0, most times what will happen is if v0 isn't exactly v and w, v0 is a linear combination of v and w. v0 is an eigenvector, or some combination of these two eigenvectors, v and w. Once we're done with that, we have c1 times x0 upper 1, c2 times x0 upper 2, and then c3 times x1, the generalized eigenvector solution. All right, here we go. So here's our 3 by 3 matrix. Let's go get what the repeated eigenvalue is. With 3 by 3, it's better just to go with the determinative a minus lambda I and set it equal to 0. What's nice is we do have this row of zeros here, or not an entire row of zeros, but we have the first row having 2 zeros in it. And so we'll expand about row 1, giving us just the 1, 1 entry times the determinant of that submatrix there, which will give us 3 minus lambda and 1 minus lambda plus a 1. Multiplying that out, what will happen is we'll have lambda squared plus the 3 lambda plus the 3 and then plus a 1 lambda. Altogether, this will combine to be lambda plus 2 quantity squared, another one lambda plus 2. So we get lambda plus 2 quantity cubed, officially with a negative on it. And therefore, 2 is an eigenvalue with algebraic multiplicity 3. To find out what its geometric multiplicity is, we go solve the system where we have a plus 2i, because lambda is negative 2. Along the diagonal, add 2. That'll give us this matrix here, and we have to find the vector v from there. What will happen actually is we'll find a vector v and a vector w if these are just some x, y, and z variables. Y and z are both free, and then x will be the addition of y and z according to the first equation. So y is allowed to be anything you want it to be, z is allowed to be anything you want it to be, and so what you do is you let variables stand for those guys. we're going to let y be equal to t and let z be equal to s. And then x then will be s plus t. And then what we do is we break that apart. This is equal to t times 1, 1, 0 and s times 1, 0, 1. These two vectors are eigenvectors. We'll call them v and w. But we're missing one. We need a generalized eigenvector to make the 3. And so we're going to build that based off of the fact that x1 is going to be from the equation e to the negative 2t v1 plus t v naught. Okay, we have these two guys though as part of our solution. C1 times this guy, C2 times this guy. We just need the C3 times x1. And x1 comes from this equation. It's our job to find the v1 and the v naught to build up x1 based off the equations that when you take a minus lambda I and square it, applied to v1 you'll get 0. But v1 is not an eigenvector itself. It's linearly independent of those eigenvectors. And then to get v naught, you do find what a minus lambda I v1 is. And so with lambda being negative 2, the matrix from the previous slide is a plus 2i. It's our job to square that matrix. In squaring that matrix, we get a matrix full of zeros. So it turns out that a plus 2i quantity squared on any vector is equal to 0. And it doesn't really matter what the vector is, but we want to make sure that when we choose it, we don't want it to be a combination of v and w. V was 1, 1, 0 and w was 1, 0, 1. So when we go pick v1, w was 1, 0, 1. We want to make sure we don't get a combination of those when we pick our v1. If we and it's totally freedom of choice here. Just make sure that it doesn't become a combination of v and w. And so if we choose it to be I 1, 0, 0, there's no way to combine v and w to give you that. And we'll check that by doing this second equation here to make sure that a minus lambda I v1 is not 0. And so we're already set up that a minus lambda I squared v1 is 0. Now we're going to check and make sure that a minus lambda I v1 is not 0 by multiplying this out. And what we'll be picking up is column 1. And we call that guy v naught. And then our solution x1 is built off of v1 and v naught. It's e to the lambda t v1 plus t v naught. So we found our x1, generalized eigenvector. This guy here is generalized eigenvector. And this guy, v naught, we said is actually a combination of v and w. It is an eigenvector. It's, let's see, how do we combine 1, 1, 0 and 1, 0, 1 to get 0, 1, negative 1? It's going to be 1, 1, 0, that's the v. And we take away the w. If we take away the w, we'll have exactly this vector that we're calling v naught. So v naught is a combination of v and w, but it's the v1 that can't be that. v1 is your generalized eigenvector. Putting it all together, then we're going to have c1 times x naught upper 1, what we had before. C2 times x naught upper 2, and finally C3 times x1. Putting this together, what we could do is combine them, where we factor out the e to the negative 2t, and we get c1 times v and c2 times w. And when it comes to c3, we put these two together and get the vector with t's in it, where we have 1 t and negative t. So this is our solution to that equation, who was x prime equals ax. It was x prime equals ax with that given a, and here's the solution to that, the full solution Okay, great.